Good afternoon, everyone. My name's Arash Mustafi. I'm the Director of TYC at Imperial College London, and I'd like to welcome you all to this very special occasion to celebrate the 15th anniversary of the Thomas Young Centre. It's also the first in-person event we've held for almost 2 years. So on behalf of all the TYC directors and the management team, I'd like to thank you all for being here. And I'd like to thank all the people joining online as well. Thank you all for being here too. The TYC was formally inaugurated on the 10th of November 2006, which is almost exactly 15 years to the date, with a highlight seminar by Professor Michele Padilla, who is one of our speakers today. So it's very fitting to have him here today again. On the topic, your seminar was on the topic of simulating complexity, challenges and progress in atomistic material science simulations. So, and I guess the theme today is similar, so we'll hear what's happened over the past 15 years on that front. We're also very lucky to have talks from one of the current TYC co-directors, Dr. Rachel Crespo-Otero. Where's Rachel? Sitting somewhere around here, I hope. There she is, over there. And also from one of the co-founders of the TYC, one of the founding directors, Mike Finnis, who's with us here today. So thank you, Mike, for being here. But before that, I'd like to welcome Professor Mary Ryan, Imperial's Interim Vice-Provost for Research and Enterprise, and Professor of Material Science and Nanotechnology in the Department of Materials, here to say a few words. So Mary, over to you.
Thank you, Arash. Thank you for inviting me to say a few words. I've now got to that age where I get to say a few words, which is somewhat distressing. I can't believe it's 15 years. We're all still very young, Mike, but a brilliant job. So it's also really nice to see you all in person and to see such a young and vibrant crowd of people here interested and doing brilliant research. So as Arash said, the Thomas Young Centre, the London Centre for Theory and Simulation of Materials and Molecules, was founded in 2006. And as you all know, Thomas Young was the last great polymath and has been described as the last person who knew everything. And I think that curiosity that he embodied, that thirst for knowledge across disciplinary boundaries, is really embedded in the spirit of the TYC as we see it today. In my job now in the research office, one of the things I'm supposed to do is encourage interdisciplinary, transdisciplinary research, understand how Imperial as a centre and as a college can work with other organisations. And we have here in our midst a really great example of how that can be done and how it can be sustained, right? It's been, in fact, lasting and growing in strength to strength over the last 15 years. It's also been instrumental, really, in marking London as a global centre in the theory and simulation of materials and molecules. And I think that's no mean feat, because this is an extraordinarily competitive scene worldwide, and we really are the centre. In part, that's been down to the extremely good leadership that we've seen, but also through just the activity and the passion of all the people that have been engaged. So this strength has been recognised by 2 EPSRC awards for the materials modelling, the Modelling of Materials and Molecules Hub, the High Performance Computing Centre, which is the UK's national HPC facility that's hosted and led by the TYC. That has over 1,000 users. The TYC itself has over 100 PIs and over 700 engaged people. It's also had 2 successive doctoral training centres, attracted a multitude of research funding, engaged lots of industry partners, and you've written lots of brilliant papers. However you would like to measure the TYC, it's been a tremendous success. In my job, I'm supposed to measure those things and tell you what a great job you're doing. But I don't think it's the right metric really to judge the TYC. And I think from day one, the way the TYC has been built is by building a strong community. And from that community, all these other great things have flowed. They're a byproduct, and they're a brilliant byproduct, but they're a byproduct of this community building. The brilliant events and community activities, the inclusive nature of the community, even to experimentalists like me. I've been welcomed at many TYC events. And I think that's another important strand of what happens in the TYC. It's how do we think about materials in general, and how do we work across these boundaries? And coupling experiments and modeling has made it a success. I'm not going to say very much more, except I hope you have a really brilliant afternoon. Congratulations on reaching 15 years. Optimistic for the next 15 and what you're all going to deliver. I'm going to have to escape. I'm afraid I've got a rather dull meeting to go back to, so I might surreptitiously join this one on Zoom. But I will try and join you later in the evening, and have a great afternoon. And I will catch up on Zoom later if I miss your lecture now. Thank you.
Thank you very much, Mary. So I'm going to ask Carla Molteni, TYC Director at King's, to introduce our first speaker.
Thank you very much. So I'm Carla Molteni, I'm the co-director of the TYC at King's, and it's my great pleasure to introduce our first speaker, Professor Michele Parrinello. As we heard before, Michele was here in 2006 and gave the first lecture to open the Thomas Young Center, and so it's a privilege to have him here again in spite of the pandemic and all the difficulties in traveling. So we're very grateful for this. Michele Parrinello doesn't really need any introduction, having contributed with many methodological advances to the field of materials and molecular modeling, which is the core business of the Thomas Young Center, with many methods like the Raman-Parrinello method for constant pressure molecular dynamics, the Carr-Parrinello method for ab initio molecular dynamics, metadynamics for non-sampling, and so many of the methods that you all and we all use. He has recently moved to the Italian Institute of Technology in Genova after many years at ETH Zurich and the University of the Svizzera Italiana in Lugano. And previously he was in Stuttgart, where I was also in the group, and IBM, Zurich, and the CISA Trieste, and so on. So he has really a very good overview of and also working in many different places. Today is going to talk about machine learning and molecular dynamics. 15 years ago, there was not much machine learning in the field. Now is one of the top topics. And we are very looking forward to hear all these new exciting development in the field. Thank you very much.
Thank you very much, and then it's nice to be here again and to see so many friends. I don't use the old friend all the terms of friendship. Also, I spent 1 year at Imperial College in the early 70s. So this place used to be familiar to me. I came around this morning, I could hardly find my way through the campus. Okay, so let's go and talk. I mean, the subject of this talk will be, I mean, the core of the talk, the problem that I'm going to address in this talk is essentially the same as 15 years ago, but 15 years later, and much progress has been done. I hope to show to you. Okay. Okay. Again, our core business has been molecular dynamics, and I don't need this audience to discuss how this is done. And the issue, I mean, one of my preoccupations in my career has been to improve this method, which is so potentially powerful. And we want to move along this axis, larger system, better potential, longer simulations, and it should not be underestimated the importance of, in the end of the day, to lead to an understanding of the system. Producing data is important, but it's only the beginning of a process which should lead us to a better understanding of the system we are studying. Okay, so let's start with the time, which is, I think, the toughest of all these challenges. And as you know, I mean, in life, there are, in physics, there are many phenomena that get far from the reach of molecular dynamics, like protein folding and phase transitions. And we want to be able to study these events. And one of the issues is the presence of energy barrier that lead to a kinetic bottlenecks, excuse me, and too long time scale. For instance, if you have a barrier 150 kilojoule, which for a chemical reaction is not unusual, at room temperature to observe a reaction will take you more than 5 days. And so we, okay, very good. I should have put. Okay. Okay. And we want to address this issue. We continue addressing this issue. 15 years ago, the methods are talking about were in their infancy. So I hope that we can register some progress. One of the first difficulties, at least in the way I look at things, being a physicist and by nature, by education or reductionist, to try to have a simple possible description of the system, and that conflicts with the reality of a potential energy surface of systems, which are very complicated. And I like to liken the potential energy surface to a kind of multidimensional version of the mountains landscape in Switzerland, where you have many valleys and many paths and so on and so forth. So we need a way of describing this complex system, and the way we chose was to use methods. There are many methods out there, and I don't want to claim that this is better than, say, method for like past sampling of similar methods. But just that's the way we look at the problem. So what we do a conceptual step. So in order to simplify the description, we want to introduce a variable that describes the slow mode of the system. We call this variable collective variable. And we calculate the marginal of the Boltzmann distribution and get the probability distribution of this variable. I think you, okay. Can you see the arrow here? Okay. So in a when you have two states, A and B, then the probability distribution relative to this variable, provided that this variable is reasonably chosen, it's a two-peaked or multimodal distribution. So if I start sampling on a configuration which belongs to this peak, the probability of crossing this no man's land is very low, very low. And so you remain stuck. There is a dual way of describing these situations. You can look either at the probability or to the free energy surface, which is the log of the probability. And this is the picture which I'm more familiar with when we look at two-state system with two minima separated by a margin. Okay, now if the situation is like that, and there is very low probability of going, we have to do something. So what we want to do is to modify the probability distribution so as in this region, probability of being there instead of being negligible as a large value. And in other terms, what most of the enhanced sampling method can be described as a way of starting with the probability distribution, which is the real one, but it is difficult to sample, mapping and map this probability in a target probability, which we can decide what it is. And the second probability is much easier to sample. So what we want to do is start with the real one, go to the target is simpler to sample, but then in the end, we have to do a reweighting to go from this probability to the real one. And this operation is called reweight. So we have to go forth and back. Example of target function. If you do umbrella sampling or metadynamics, you start with the probability which is to be model and get, your aim is to get into a flat probability. Well tempered can be a bit more sophisticated, rather than aiming at getting the right the flat distribution, you aim at getting a smoothed version. It's like if you took the mountains of Switzerland and you transform that to the rolling hills of Devon. And the latest evolution of metadynamics is written here. It's OPES, and let's spend a few words on that. So OPES is a kind of uses a lot of the tricks and the insight that we got over the many years in which metadynamics has been around. And say you want to gain, to aim at going from this difficult probability to a more gentle probability, and you want to go back, as I had underlined. So in metadynamics, what you normally do, you change on the fly the bias potential that you add to your system to push the system out of the minimum. In OPES, you focus your attention instead on the probability distribution. And this is the great advantage. If you look at machine learning or statistical books, there are lots of papers on how to represent the probability distribution. And so this makes this method much more controllable, smoother, and more efficient, and that's what we use nowadays. Again, this is expressed as a sum of Gaussian, but how they're built and so on, that's not for this talk. Okay, but one important outcome, corollary of this way of looking and on the method, and also of the fact that we look at there's an unsampling method as a way for changing the distribution, is the fact that within the scheme you can we have done this in this paper with Michele Vernizzi and Pablo Piaggi. We have demonstrated that most of the non-sampling method can be framed in the in the way that OPES is framed. And for instance, you can do very simply multi-thermal, multivariate simulation. So suppose you have a phase diagram, okay? So if you use a standard canonical simulation, then you sample each and every point in a grid, and then you interpolate and you get information about this region of the PT phase diagram. With this multi-thermal, you only, if you want to sample the same region, you don't need to do n simulation. One simulation is enough. And the cost of the one simulation is slightly higher than the standard simulation. So you buy one, you pay one, and you get n. Okay. Okay, so the key ingredient for this method is the reliability of the collective variable. And first of all, I mean, we want to ask ourselves if there is a way of defining properly, rigorously this collective variable. And the literature, there are many suggestions. You can look in the free energy surface and look for free energy pathways. You can look at slow relaxation mode. We'll discuss this way of going about things in the next slide. And formally, it's believed that the isocommitter function is the best CB possible. However, all these things require that you already know the transition state, you know the dynamics and so on. After the fact, you can get the CB. But if you don't know, that's a problem, okay? And for this thing, we have until recently tried to build CB on physical intuition and other heuristical approaches, which I don't think it's not an approach that should be looked down upon, because, I mean, if you get a CV through a physical reasoning, then you really have solved your problem. Okay. So we decided to use machine learning. Machine learning, of course, are based on data. Where do we get this data? Okay, so there is a situation where you can get a reasonable number of data when you have, suppose you know that the surface with several metastable state, and imagine that you know this metastable state. Oops, sorry. Then you can run a simulation in all this minimum, and this will be your data. Okay. Now we want to use this data to construct CV. Okay, so. And so this is essentially the same concept, but in more pictorial way. So this is what we know. So we have metastable state. So we know this island, we know this other island, we know this other island. So what do we do? And we have data about the different islands. Okay, and so the first thing that we want to do is to try to discriminate between situations which are of this type. That's a chemical reaction. That's a the freezing of, I think it's silicon. And so we collect data here, collect data there, and then we want to enhance the sampling in the direction that maximally separated the two states. And there are methods out there. The simplest is the Fisher linear discriminant analysis. But I mean, nowadays, you do a much better job if you use the non-linear machine neural network version of this method. So what we do here, we have a set of descriptors. They describe the system. So this being distances between the atoms, angle and name. And you collect the data in state A, then you collect the data in state B, you send it to machine learning things, you go through the layers, you optimize what you have to optimize, and you start with a situation in which you were not able to discriminate in any generic description. You cannot discriminate the data, but you go through this procedure, you end up discriminating well A and B, and eventually you really have a good discrimination. You can use this direction as CB. There are, I mean, one could spend a lot. These are very good a good CV. And there are reasons, it's a bit strange, but there are reasons for why it is. But they are not perfect CV because they don't have any information on the slow modes or the transition state. So we want to be able to get to feed this information into the CV, because discriminating it's only the starting point. And so for that, we use the so-called variational approach to conformational dynamics. So we look at the operator that evolves the system. This operator will have eigenvalue and eigenvectors. And there is a variational principle, which involves the time correlation between system at time t and system at times t plus tau. I mean, there is a variational principle. It's normal when you have operators, you want to find the eigenvalues, and the eigenvalues, for instance, in quantum mechanics, is a very loose principle that allows to do that. It's just a generalization. So you can use, like in quantum mechanics, a linear combination to express these eigenvectors. But I mean, now we are in the time of age of machine learning, and we don't need the basis set. We train a collective variable. We train a neural network imposing that this eigenfunction, the eigenvalue, is as large as possible. Okay. But again, we are faced with the same problem. So if you have the dynamics, you have solved the problem, and you can get the CV. But then getting the CV is extremely useful, but will not allow to go back. So if you get the CV, you can do the reaction. If the reaction, you don't need, you can get the CV. But you, so this. So the way we go about it, we use an exploratory non-sampling simulation, maybe with LDA, maybe with some other methods, like we can do also with parallel tempering, whatever it is. So you collect a certain number of events and extract the slow mode with this method. Of course, if you applied bias, you have to do a reweighting, and then you get the OCD and you remove the. So this is incredibly efficient. Just for the aficionados, so they know that this little protein is a testing system, and it has two states, A and B. The natural collective value would be phi. I suppose that we are stupid or ignorant, and we use this direction. We push in that direction. And of course, if you do that, the system has a lot of difficulty in going, it's the same thing, in going from one minimum to the other. But if it goes through this procedure, then it goes up and down in a very short time. You see 10,000 nanosecond here, very quickly you get your result. Not only that, but since you put the information about the transition state, the system is pushed in a more natural and physical way from one state to the other. And that's reflected, for instance, in this is a problem of crystallization. I think that's, I don't know what system it is, maybe sodium or something. So if you use the discriminatory CV, it goes and it's not too bad. You can get the difference of free energy between one and the other, but it goes with a certain difficulty. Instead, if you use this transition state informed CV, then it follows closely the physical things where you go from liquid, you nucleate, and you go to the crystal. Okay, so let's go to the accuracy. I'll show a couple of examples, not all of them, from the study of phase diagram of complex material. In this case, you have silicon, gallium, phosphorus. So this is a system where there is a change in bonding from covalent, or the bonding itself is rather subtle. And if we want to do that, we have two issues: time scale, and the other is the interaction potential, which we don't have. So and we could do ab initio, but that's expensive, in spite of the acceleration that this method provides. Some time ago, it's almost the same age as Thomas Young Center with Bella. We thought that we can use machine learning, which then were there in the infancy as far as application to physics were concerned, to essentially fit the potential using machine learning. And it's not immediately trivial because you have to respect the translational and rotational invariance, permutational invariance, but we had a little trick. But nowadays, there are much more sophisticated programs and a variety of programs. In those days, it was a bit clunky and took a long time to get potential. Okay, again, these methods are based on data. So if we want to study phase transition, we need data for phase A, phase B, but also for the transition state, because nobody, neural networks are good at interpolating and poor at extrapolating. So if you don't have information here, you're in trouble. You can be in trouble. And so you want to get the info. For that, we generate, so training in this field is essential, and the data that you feed, they are essential. So we generate configurations of the transition state using chip model, then we got that. And this has been very, I think, extremely successful. And I'll show two examples if I have time, quickly. One is gallium. Gallium is a very peculiar metal. It has a very low fusion point. It has a bonding which is a mixture of covalent and metallic. It melts in your hand, and the density is a density anomaly like water. Okay, and it has a polymorphism. Okay, so at least 3 phases and more. Okay, so now training is difficult. So what you do, you start with one guess, then you do, and then you add more data, and then you go further until you're satisfied that you have reached convergence for all these phases. I mean, you have a ACV that's able to describe well. And in this process, the use of multi-thermal multibaric has been crucial because it allows us to get a lot of different and non-correlated information. These are the results. I would say it's pretty good. The scale is the energies involved are very small, and so that's quite remarkable. But we can also explain another feature of gallium. So gallium can be undercooled extremely, and up to a certain temperature, it undercools in the beta phase rather than the alpha phase. And above that goes the system crystallizes when undercooled into the alpha phase. And we studied this process. we don't have much time to go into the details, but you can see here the barrier for going from one phase to the other at the low temperature is the alpha, at high temperature is the beta. So in spite at high temperature is the alpha that should be favored thermodynamically, but there is a kinetic effect. And we were, after publication, we got a message from a colleague from Stuttgart who studied gallium for a while, and we read these magic words. What we did is in agreement with the experiment. If I have time, or I can skip 5 minutes, okay, fine. So the other example, which I also find particularly dramatic, is the case of phosphorus. Phosphorus in the liquid state exhibit a relatively rare phenomenon, that of liquid-liquid phase transition. So always, and there are two phases: a low density phase in which phosphorus forms this tetragonal pyramids, and in this phase is an insulator. Then there is it goes through a first order phase transition, so you can see here, and it goes into a polymeric liquid where it is metallic. So the question is, can we simulate this? And that's for us, but also there have been speculation that this liquid-liquid phase transition would terminate into a critical point. And so we want to study the property, confirm, draw a phase diagram, and see whether there is a phase transition and what are the properties of this critical point. Again, the procedure for finding the potential has been lengthy, but in the end, you have to do self-consistent things. And this is the phase diagram, how it is drawn. We have this multi-thermal, multi-baric, so we can calculate easily at different temperature and pressure the free energy surface as a function of the order parameter, which in this case is the volume. And we find that at a low pressure, the low density is favored. Then it goes through a transition. So this is the line of 2000. So we are exploring this line. So here, the low density is more favorable. I cross the phase transition line, and then I go into a situation in which the other phase is favored. So then now we go and see whether there is a critical point. And so for doing that, we move along the coexistence curve. So, and we find that, say 2000 or whatever it is, there is a barrier. So we have first order phase transition. Then we increase the temperature and pressure, and the barrier decreases until we go to 0, which is the critical point. So we can calculate the critical point. We do proper things, the scaling with the number, whatever. We use techniques which are well known in the theory, but never applied the system of such complexity. It is very interesting to look at the transition at the critical point, where the free energy, of course, is flat. The system can undergo very large fluctuations from high density to low density, high density, and at the same time, the electronic structure changes. In high density, there is I'm a bit mystified. One, high density, there is a confusion with the colors. At the Fermi surface, there is high density of states. Then when I go to the low density, the density of state is zero. So it goes from metallic to conductor, to metallic to insulator. And the same time, as it goes from metallic to insulator, the structure of the liquid changes. Because with this kind of polymeric structure, the first P4 units began to appear, and then they become dominant in the final thing. Okay, so we have developed to solve problems like this. There are chemical reaction in solution and other fantastic applications, which are a kind of the dream of my scientific life. Would have been defined as being able to simulate this system where fluctuations and electronic structure play one against the other. So we publish our paper. I mean, our method, the programs, and so on. You can get it, and you don't have to pay anything. We can do multibaric, multi-thermal, efficient, recommend opens, and I don't have time this time round or way of calculating the rates. And I have to thank always my group, which has been the heart and soul and the brain of what we do. I would, I like to quote this verse from, it's in Spanish, from a poet of last century, which means, in a very poor translation, says, traveler, there is no path. You make your own path as you go. And with that, thank you for your attention.
Thank you very much for this very fascinating talk and so many different systems. Are there any questions? Please.
Yeah, so thank you for a very interesting talk. I was impressed by the agreement in the case of the phosphorus system, the agreement of the experimental data theory. So
Me too.
maybe you mentioned it and I missed it, but what was the underlying ab initio theory that you used for the training to create the training?
Oh, in the phosphorus, yeah. I think, I don't remember, frankly, but I think it was SCAN, SCA.
Okay.
Other questions? Hi.
Got a question from GP about time related metadynamics. We have calculated that isomerization rates of proline in the protein environment. The well-tested metadynamics is employed.
Can you take off your Amazon? Yeah, thank you.
Successfully made the isomerization happen and got good free energy surface. But when we re-weight time, an extremely big value. I was looking into the algorithm of time re-weighting with the bias at each step is about 28 hours per mole. Re-weighting time was very big, the bias was 24 hours per mole. Re-weighting time.
Okay. So I suggest that you write to us with all the details, and we see whether they can make a diagnosis, because in this way it's impossible. Thank you.
I think it's too detailed.
That's on the chart.
That was a question for the chat.
Yeah.
It's a bit too detailed. No.
Yeah. Okay. Anyway, I suppose that the question was about how diffusion can be metadynamics method for calculating kinetics and weights. So you didn't talk about the.
No, I didn't, but okay. I thought, how about real time? Okay. And so because we have this problem, we have the next level potential. So the dynamics is useful for sampling, but it's not the real dynamics. So the idea was based on very old paper of Water a long time ago, where he noticed, pointed out, if no bias deposited in the transition state, then, so if you are able to do something like that, so you got the bias, you make flat in one well, flat in the other well, but you don't touch the transition state, there is a simple relation between the time that you measure in your bias molecular dynamics and the real time. And so that's the relation. In a rare event scenario, the distribution of these times must be of Poisson type, because it's like alpha decay. It's one event is uncorrelated from the other, and this provides a check of the assumption made, and now we have more checks and so on. And this method, there are several variants of this method. I believe that the most efficient is this Gambes by, I like in particular, this is the young lady, and she has been very good. She gets a PhD now. That's it.
Okay, thank you very much. Any other questions? If not, let's thank again Michele.
So I'm going to ask Jochen to come and introduce our next speaker.
Hey, thank you. Well, it's a great pleasure now to introduce our next speaker, Rachel, who is here in the first row. So Rachel grew up in Cuba, Havana. And this is also where Rachel studied chemistry, I believe. And you also did the PhD there. And during the PhD, Rachel did sort of the first contact with sort of mainland Europe, right? That was a collaboration with a team in Spain, in Madrid. And then the journey continued sort of slightly sort of eastwards, northeast towards Germany, where Rachel did a postdoc with Mario Barbati, who is one of the leaders in non-adiabatic molecular dynamic simulations. I think that was also, in the big group of Walter Thiel, I remember at the Max Planck Institute. And after that, she had a short stay with Aaron Walsh, actually. But that was when Aaron was not at Imperial, but still at Bath. And 2 years afterwards, Rachel received a position at Queen Mary University as a lecturer. And this is where she still is and does her research. So she got recently promoted to senior lecturer. So her research is in the area of simulation of excited states, non-adiabatic dynamics. So she is also an active developer of the Newton-X program that maybe some of you know, and doing exciting work here. I think this is also broadly the topic of Rachel's talk today on modeling photochemical processes in molecular crystals. Rachel, please come forward. Thank you.
Thank you very much, Johan, for the very nice introduction. And I'm very happy to be here today. And we are celebrating the 15th anniversary of the TYC, which is a real great thing. So I'm super honored to be here giving a talk and sharing with Michele and also with Mike here and with all of you. So I'm going to talk a little bit about some of the work that we've done in modeling excited states in molecular crystals. And I call this talk like modeling photochemical processes, but I mean, we cannot really say that they are just photochemical processes because we have also photophysics, we have transport, we have a lot of things going on. So what has been our main interest? Okay, first, our main focus has been to focus on trying to understand what happens to the photochemistry of a molecule when you move from the molecule to the dimer to the crystal, and how the crystal environment can modify the, in general, excited state localized processes that happen at the level of the molecule. And we can think about different kind of processes. We can start thinking about what has been called emission quenching. The reason of emission quenching is like there is a lot of processes that occur at the non-radiative level that are going to be related to either the overlap between the nuclear vibrations, vibrational wave functions, or because the existence of conical intersections that just happen in the regions of very strong couplings between the vibrations and the electronic wave functions. So emission quenching will happen when you find either charge transfer states that will generate this kind of conical intersections on just when you have like very strong interaction between the vibrational wave functions. So other processes that could happen could be you could have processes that are related to the formation of cavities in the solid that will restrict in a way the motion of the system. So I just wanted to illustrate in the next slide some of these non-radiative processes that could happen, and in particular what you can have if you have a charge transfer state. And charge transfer states play a very relevant role in photochemical processes in solid state because they will couple with vibrations that in many cases are related to distances between the two molecules and will take in many cases the systems to the ground state. So if we see this very, this is a simulation that I've done quite a lot of time ago on the dimer of methylformamide. And I think it's a good example of what could happen when you go from the molecule to a dimer. Essentially, you excite your system at a local state. You have the electronic density on one of the molecules. This is a local excitation. And you put the system here. So when the system gets the energy, you have like the crossing with the charge transfer state that is coupled with the motion of the proton from one molecule to the other. And because of that, you will get to a region of the potential energy surfaces where you have like the crossing between the first excited state and the second excited state. This process won't allow the radiative decay, and because of that, you will have like the system won't show fluorescence or phosphorescence. So this is one of the kind of processes that could happen. What could happen as well? In some cases, and this will be limited cases, it's not very common, but also happens, and it generates a lot of interest in the last few years, essentially because it's the opposite behavior. It's what happens when you put the system in the solid state, and in that case, instead of having a decrease of the emissive response, then you have an enhancement. And that essentially could happen when you are able in the solid, and because of the interactions with the molecules around the central excited molecule, you can restrict the access of these conical intersections, or because you can just decrease the overlap between the vibrational wave functions between the ground and the excited state. So we've been looking at a lot of systems showing this kind of behavior, try to understand it, how you can maximize the emissive response in the excited state, how you can try to avoid the decay through conical intersections. And I'm going to show you a couple of cases here related to that. And just want to illustrate some of the systems that we found. We have like a collection here of flexible molecules. These molecules are quite flexible. However, when you put them in the solid, you will find that they will emit light quite brightly. And the reason for that is essentially because you will have blocked the access to these conical intersections. There is something here that is important to take in mind. And it's like, for those who are familiar with inorganic semiconductors, we are familiar with the idea of transport through bonds. But in the case of solids, the transport happens in general in a different way. Essentially, the transport is going to go through incoherent hopping, essentially because the excitations are clearly localized on a single molecule or on a few molecules in the system. So a good way of checking that, and that happens for most molecular crystals, is looking at the values of reorganization energies, and just to have an idea of how much the relaxation that happens in the system in the excited state can compete with the values of the exciton hoppings that will give you an idea of how important the transport will be in comparison with the localization of the excitation. And you will see that for this set of systems that we have here, and as I mentioned before, we have a lot of rotable bonds here, we can have systems that can really access conical intersections. You will see that for most of the system and for all of the systems, you will have like the reorganization energies will be significantly larger than the values of the exciton couplings. And because of that, we can talk about very localized excited state processes in these systems. So just to show you some typical conical intersections for some of the systems, and here illustrating some typical aromatic systems where you have a set of aromatic rings that can just pucker or can rotate around a single bond. And you can see that for these systems, you will have an increase of the energy of the conical intersections when you go to the solid state. Again, this is related with this cage effect that you will have in the solid. And also because of the interactions that the molecules can establish with the molecules that they have around. We have other kind of systems here. We have systems where you have excited state proton transfer. And in that case, normally you have a coupling between the proton transfer followed by the rotation around a single bond. And this rotation is going to be also in many cases restricted because the environment that you have in your system. So one question for us who model this kind of systems is, okay, what's the best way of describing excitations when we're talking about organic crystals? And of course, we have like the, okay, do we use localized or delocalized methods here? And for us, we've seen that the best choice is use localized method just because of the features that are described before, because the excitations are clearly localized. But in a way, we shouldn't forget that we have a crystal where we have long-range interactions with the periodic system. So this electrostatic interaction will still affect the photochemistry of the system. So to deal with this situation, we've been using methods that are based on the eval embedding approach. These kind of methods, essentially, what they do is like they start using a periodic boundary condition calculation where you can obtain the electrostatic potential in a particular cluster in your system. You can extract this cluster and you can select different regions within the cluster. And for these three regions, in this case, you can do it in a different way, but this is one of the most common ways of doing it. What you do is like you change the charges of the third region of your system in a way that you are able to reproduce the electrostatic potential of the whole solid in the central region. In that way, you keep the description of the long-range interactions and you can still keep this periodicity of the crystal in a way. So we've been using these methods. We have put this together and try to add some extra interactions to take into account. Also, I need a bit of water. Also dispersion and sorry. So with we've implemented these methods in a way that we use 3 calculations, and we use a subtraction methods in a way that we can consider the other interactions rather than the electrostatic part at the level of the ground state of the system. And a student who did the PhD with me put this together in a code that is called Fromage. The student is called Miguel. He's actually a lecturer at UCL. And essentially in the code, we implemented a set of tools that will help you to analyze and understand excited states in molecular crystal using this kind of techniques. So the methods use different electronic structure techniques, and we can select different methods to calculate the central part in your system and also the QM prime part. And from the central part, and I think this is a good feature, because for the central part, this allows you to use multi-reference calculations. And multi-reference calculations are extremely useful when we are working with conical intersections between the ground and the excited state. And this is because single reference methods that like TDFT are not able to describe properly the crossings between the ground and the excited state, because the monoconfigurational nature of the ground state using TDFT. So in many cases, if you want to get like the right energetic and get the right energy barriers to be able to study a particular mechanism, you need to go to multi-configurational methods. And in many cases, we needed to use CAS-SCF, CAS-PT2, and all these methods. Fortunately, if you are working with systems that develop their chemistry only in the excited states, TDFT could be enough for them, because there is not any restriction in the description of crossings between excited states. And essentially, as you have a very good description of the crossings in the excited states, you can use TDFT for these cases. So I'm going to talk now about one example that we've been looking at recently, and it's related to the photochemistry or the photophenomena that happens after excited carbazole, crystalline carbazole. Carbazole is a system. It's a molecule, it's a very simple organic molecule that can be used as building block in many optoelectronic applications. And an interesting thing about carbazole is like it shows ultra long excited states lifetimes. It's something that is called afterglow materials. Essentially, you irradiate them, and after illumination, they stay emitting light for a long time. And the reason for that is not completely understood. So another good feature of carbazole is that it shows room temperature phosphorescence. And for many applications, it's good to have phosphorescence at room temperature. So it's interesting to look at the reasons for that behavior. Something interesting that experimentalists have found is like, there were like different kind of reports about these molecules. I mean, different groups reported different quantum yields for these processes, and that seemed to be related to impurities of defects in these systems. And a recent work is from the beginning of last year that appeared in National Materials, analyzed the effect of impurities or organic dopants in these processes. And they did a lot of experiments trying to find out, and we then went back to the processes and tried to understand what was going on. The first thing that we did was to try to understand the molecule center mechanism there. And if we just focus on carbazole in the crystal environment, you will see that the molecule, when you excite the molecule, you will put the molecule in the first or second excited state, depending on the wavelength that you use to excite. Then you will have relaxation in your system, and you will have intersystem crossing to one of the triple excited states that we have here. So once you have this transition, that if you excite directly to S1, you will find the third triple state, the triple state will find a conical intersection in the excited state that will allow the relaxation to a second triple state. And depending there on how the relaxation happens, you may have like the system can relax in this branch of the potential area surfaces or this branch. And depending on where it relaxes, you may find emission of longer or lower wavelength. And in fact, in the experiments, they find that this kind of molecules show kasha, that is like the regular emission from the first triple state or non-kasha emission. And essentially, if you calculate, if you look at the spin-orbiting couplings in these systems, you will find that the values are extremely small, but still the process is facilitated by the high density of excited states that you are here. So that you have here. So we use a semi-classical Marcus-Lewis-Jottner theory to calculate the rates of the different processes that happens in this system. If we are talking about calculating the rates for intersystem crossing, the coupling element that we need to consider here is a spin-orbiting coupling. And to calculate this factor F that will consider the ability of the quantum modes to participate in the process to tunneling, you can get that the values of the predicted times and intersystem crossing, the times can be got from a simple relationship from the constants, considering the different processes that we have here. And you can see that the values predicted are very similar to the experimental one. The ones in parentheses are the ones that we get from Marcus-Lewis-Jottner, and the ones that you get here are the ones from just using Marcus without considering the quantum modes. Okay, so you can see that the agreement with the experimental values are quite good. Essentially, we can say that the mechanism that we are proposing is fun. Essentially, we have initial excitation to the ground state, relaxation, a triple state, decay through that triple state, and then we can have emission from either T1 or T2 state. So what happens when we move to the solid? When we move to the solid, in the solid, we will have different kind of dimers. We will have different kind of configurations of one molecule with respect to the other. And you will see that in these systems, the value of the exciton couplings are extremely small. The larger value of exciton coupling is 23 mega electron volts, which is a very small value. So the idea that was in the past proposed that the reason for ultralow phosphorescence was the strong interaction between the dimers in the solid doesn't seem to be right. And in fact, if you calculate the constants that I showed you before, using the dimers, you will get very similar values that you get for the monomer center process. So essentially, that seems to show that dimerization is not the main process here, or at least the formation of dimers between the carbazole molecules is not the main process affecting the ultralong phosphorescence response of this system. So what other kind of processes we can have? And I talked before about exciton couplings. If you look at the triple states, for example, and try to find Frenkel excitons there, you will see that you don't get like typical delocalized Frenkel excitons. Essentially, what you get is a very localized excitation on one of the molecules. And under these conditions, the main mechanism that will be related to the transport will be Dexter energy transfer, where essentially what you have is something like this. You have your system with this electronic configuration. You may have like the transition of one electron from this state to this one, and another electron from here, and you transform a triple to a single, and you keep the triple, you keep an excited triple state. If you calculate, and in this case, with this calculation using constrained DFT, if you use constrained DFT here, you can get the values of the couplings. They are also very small. However, if the lifetimes of the triples are a little bit longer than singles, still the process could be important here. So if we try to put all of this information together, we can propose what could be like the exciton pathways that we may have in these crystals here. And you can see that if you follow the excitons will follow pathways that are considered dimers A or B, or you will find also a exciton transport pathway along like a linear line of C dimers. Now, what happens when you consider the presence of the isomers in the system? Essentially, if you try to find charge transfer states in these dimers that I showed you before, if you try to optimize charge transfer states here, you can get them. In fact, some of them stabilize a little bit, but they are quite high in energy. So what happens when you have like this impurity in the system? When you have the impurity in the system, essentially the energy of the charge transfer state really gets very low. So you expect that when you excite the system here, this charge transfer state can be populated and can start in a way to facilitate the process after the initial excitation. Just to go a little bit more into details in what could happen here. You will have like the molecules that is initially excited, the molecule of carbazole. If you calculate the energy levels of the impurity here, you will see that it's going to be a little bit higher in energy. So you expect that the charge transfer is, the electron transfer is going to happen in this direction. And you can see that in that case, what you will get in the end is a charge transfer state where you have, okay, carbazole with a minus, with an extra electron, and the impurity with a plus sign, I mean, with a hole in the system. And if we look at the electronic densities at the beginning of the process, you can see that it's true that at the beginning, the electronic density is localized on the carbazole molecule. And if you look at the fissure of the charge transfer states, you will see like the separation of charges when you have the interface. So what happens next? What's the next part of the process? Essentially, the charge is most likely trapped on the impurity on BD here, because you don't have way, because the alignment of the energy level of moving this positive charge, so it's going to get trapped on the impurity, and then the negative charge can't transport through the crystal. And you can think here about different possibilities. We can think here about the possibility when the negative charge finds an excited single carbazole, and depending in fact on the and this is, I mean, this is just a representation, a graphical representation of the process, because what you get in the end on the transfer will give you whether you get a triple here or a single. But essentially what this shows is like when you have like the interaction between the negative charged carbazole with the excited carbazole, even in the single, on the triple excited state, what you will do is like you will keep producing excited states. So if these two systems interact, you will have like what was initially a negative charge system, now it's going to be an excited molecule. And this excited molecule could be either in the single or in a triple state, depends on the electronic configuration that you have at the beginning. And essentially this is a mechanism. The first, this mechanism will help you justify delay for fluorescence that is also found in carbazole. Is less, it is because of the lifetimes of the single states, is less important than ultralow phosphorescence, but it also happens and is being detected experimentally. And you can also justify like why the excited states of carbazole are ultra long. I mean, why they stay for a long time. Essentially, every time that a charge, a negative charge carbazole find one excited state, you can have this electron transfer process that can in a way enhance the lifetime of the excited state. And this is, we calculated also the rate for this. And I mean, we calculated only for the interaction between the negative charge and the ground state. You can see they are quite fast. So this is something that can happen. And we think that in a way can help explain why these systems can show ultra long phosphorescence. Okay. So how long do I have? Couple of minutes, okay. So I just wanted, I have a couple of examples more. I wanted to show you another system here that we've been analyzing that is related to dual emitters. And this kind of system emit light in solution and also in the solid state. And this system here, one of the chromophore of these systems is carbazole. It's a system that has the donor pi acceptor pi donor configuration. And they are very interesting in a way because even when they have carbazole here, because of the localization of the excitation at the beginning of the process, carbazole is not really involved at the beginning of the excitation. And what happens here is like after initial relaxation, the system, depending on the environment, can get trapped and won't be able to pass from one conical intersection to the rest continue the whole process. You excite here your system, you go to S3, you relax and you find a conical intersection with S2, and you can relax to the S2 minima. But the transition from the S2 minima to S1 involves a conical intersection that is a little bit rotated. If you are in a media here that with high viscosity, this transition could be hindered. So in some of these systems, and you can see that in practical terms, when you move to to media with high viscosity, you can also see two emission bands for this kind of systems. We also calculate the solids here, and you can see that you have also like significant reorganization energies. You have values of exciton couplings that in this case, because of the more effective interaction between the central part of the systems are a little bit higher, but still not won't allow to have a more effective transport regime for this kind of system. So thank you very much for your attention. I had another example here, but I'm going to skip it. I would like to acknowledge the people who did the work. Some of the students that started with me when I started at Queen Mary, they are not working with me anymore, but most of the work that I did at the beginning is because of them. Michael, Miguel, and Liliana, who is here. And the people who are currently working with me, Federico, who is attending virtually, and Amir, who is here, and also Anna, and some of my collaborators for Queen Mary, and also experimental collaborators in Mexico, also in QMUL, and Steven Lopez in the US, who is collaborating with us in the implementation of surface hopping with these embedded techniques that I described before. So I hope that I convinced you that the photochemistry of molecular crystals can be interesting in a way, and that the use of excited state localized methods can really give quite a lot of information for this kind of system. So thank you very much for your attention.
Rachel, are there any questions for Rachel? Sarah, please.
There is a lot of interest in the photophysics of molecular crystals. And I'm sure you get a lot of people coming to you wanting to do calculations on molecules far bigger than carbazole, where you can be multifold as whether even one molecule, what quality of wave function you can do. And then, as you've shown, you can have very long exciton chains. You can have a whole range of surrounding things in the crystal structure. And they may not even thought about whether they've got impurities in their experiments. What sort of size of system or what sort of considerations are there on whether you think you even start trying to help them?
Thank you very much for the question. In fact, I mean, we are dealing quite a lot with that, you know, we in fact get a lot of interest. I mean, so many people come to us to look at different crystals and that. At the moment, you know, we are working with systems, we are, you know, 30, 40 atoms more or less at that time using TDFT or, I mean, in some cases CASA-CF, but with very small active spaces. But now what we are trying to do is to move to semi-empirical multi-configurational techniques. Till used for a long time OM2 with multi-reference methods, and they work quite well for this kind of systems. At the moment, we are trying to implement a FOMO-CI. We've got the call for Granosi from Pizza, and we are trying to work with this method quite a lot. Essentially, it allows to work with bigger active spaces, and also as it is a semi-empirical method with bigger systems. And I mean, I think it's the direction to move, because as I mentioned before, the main problem that we have here is like, if we want to describe crossings with the ground state, we really need to have some kind of a multi-configurational description. So it's what we are doing here. I'm pretty sure there are other methods that can be used. I think that some people are working with DFT multi-configurational methods. In the past, we use a little bit DFT-CI. But I think the semi-empirical approach, trying maybe to reparameterize some of the Hamiltonians and try to combine this with multi-configurational techniques can help a lot.
You looked at the crystal structure and have that as some guide.
Yes.
Yes.
Yeah.
Any other questions? One of the virtual participants. Rachel, I have a question about timescales. So because you were mostly discussing it as if the molecule is sort of a vacuum as a book. So what's not much difference between the molecule or the crystalline environment? So maybe,
In terms of time scale.
So I was wondering, surely at the beginning, if you excite the crystal, then you excite it to the excitonic band, and then you then the states are delocalized, I guess, and then it's probably a question of time scales. How fast does the space of the crystal reorganize so that it localizes the excess charge, and how fast are then actually radiative transitions compared to that?
The crystal environment, I think that it tends to make everything slower. And I mean, in terms of vibrations, for example, and rotations, I think that I would expect, you know, something like in the order of 50, 100 femtoseconds of difference. In terms of for example, if you want to see a rotation, because you will have, you of course will have like the, you know, the environment kind of pushing back, you know, and but yeah, I think more or less in that order I would expect.
So the relaxation is much faster than the radiative transition.
Yes, yes, yeah.
If not, then I think we'd like to thank Rachel again.
Okay, and I'll invite Adrian Sutton to come and introduce our final speaker.
So I have the delight of introducing Professor Mike Finnis as our final speaker. Mike came to Imperial in 2006 when he became the first director of the TYC. At that time, there was only one director before we had co-directors in the separate institutions. And one of the first tasks that he faced was a name for the center that we were setting up. And as you can imagine, there were lots of rival choices, but it was Mike's brilliant idea that we should call it the Thomas Young Center, which was almost universally appreciated and accepted by everyone. One of the notable exceptions to that was a rector of this esteemed college, who in 2009, so you can work out who the rector was, said, "Who the hell is Thomas Young?" So that just goes to show that even people who rise to the very top in academic institutions can be complete ignoramuses. Mike is one of the, he's quite exceptional, I think, when you look at what happens in computational materials science. Most people in computational materials science develop methods based on existing theory. What is special about Mike is that he dares to go where no theory exists. And he then develops the theory, and then he develops the computational protocols to implement that theory. And he's done this over and over again. So, for example, almost 40 years ago, he developed the Finnis Sinclair potentials for BCC metals, which remain to this day the best way to simulate multi-million atom models of BCC metals. He then went on to introduce the essential contribution of the electronic contribution to heat conduction in irradiation damage, because until he did that, metals were being treated in the same way as insulators. And this was an absolute breakthrough in the modeling of radiation damage in metals. He developed the theory and the computational protocols for modeling metal ceramic interfaces from first principles. And that was another major breakthrough. He developed something which one of my metallurgical colleagues back at the University of Pennsylvania described to me as something that he had been looking for half a century. He developed a general first principles scheme to predict embrittlement at grain boundaries in metals by impurities, something that metallurgists have been really exercised by for probably the best part of a century. He introduced chemical potentials into first principles simulations of open thermodynamic systems, what is today called ab initio thermodynamics. And most recently, he's developed accurate models of the thermodynamic stability of materials at very, very high temperatures, so high that in fact it's almost impossible to actually make measurements of those properties. His impact, as you can imagine, has been incredibly wide-ranging. And this has been recognized. The Institute of Physics has awarded him 2 very significant prizes, most recently the Neville Mott Medal and Prize in condensed matter and materials physics. And I'm absolutely delighted that this year he was elected to the Royal Society. So he is now a fellow of the Royal Society. Today, he's going to talk to us about local and non-local models of diffusion. Mike.
Thank you for that embarrassing introduction. Just saying. I'm going to talk about something that's is really of fundamental importance in materials. It's probably
you know, it dominates material science, does diffusion, just about everything. And it's interesting and not well understood in many cases. And I just sort of noticed over the last few years, I seem to have been doing projects that have a lot to do with diffusion. So I thought, well, I better talk about that. And so I'm going to basically, now when I was a physics student, I didn't learn much about diffusion. And I'm hoping at least some of you are as ignorant as I was, because I'm going to give some introductory material as well, and then walk you through very quickly about 3 project areas which have really interested me and I've had a lot of fun with over the last few years. And so if we go back to, do I use my finger to it as a pointer on here? Do I have a cursor or anything? Can't see it. Can I do presenter view? Let's see. Okay. We can see your cursor. Oh, okay, I'll put up with that. So you got to go back to Fick's laws, and Adolf Fick in about 1850s, who gave us the famous law of the flux proportional to the gradient of the composition, or the concentration rather. And then along comes Einstein in that Anno Mirabilis in 1905, and he actually says in the paper, it's possible that the movements to be discussed here are identical to those of so-called Brownian motion. That sounds a bit disingenuous to me, actually, because, I mean, he's quoted, and this was the fundamental paper that explained Brownian motion, and was actually a blow to the many atomistic deniers who were around at that time. In spite of the absence of social media, there were still a lot of fairly eminent physicists around who denied the existence of atoms. He also showed that the flux was proportional to the force on a particle, a flux of particles proportional to the force on them, with a coefficient involving the diffusion coefficient, which of course is interesting. And about 3 years later, Parrinello in France did these beautiful experiments on Brownian motion and verified everything Einstein had predicted. So that was jolly good, but then Einstein must have got distracted by this airy-fairy stuff about relativity and quantum mechanics. So we had to wait another 25 years or so before, I can't read my own titles here, because I've got this silly panel on top of them, but I think my title probably says Onsaga, yeah. Onsaga came along and realized the connection between fluxes and the driving force of chemical potential gradient. And this is what was so useful in material science now, because material scientists are working with chemicals and chemical potential gradients. And this is what plays such a part in so many processes in material science. I've listed just a few off the top of my head there. And you can see, of course, in an ideal solution, the chemical potential is given by this simple formula here. And so when you do that, take the gradient of that, you recover Fick's law, the gradient of the concentration. In addition, you've got this driving force term, which is the electric field in the case of charged particles, which comes into play in ionic systems. And I found this equation disturbing, of course, when I first met it, as I hope most people do, because I learned and I taught that chemical potential itself is only an equilibrium property. You know, like entropy, it's a property of a system in equilibrium, so it has to be the same everywhere for a component, and also I learned not to mix up atomistics and stuff with thermodynamics. And I think there's a shadow of those atom deniers still operating decades later, who teach thermodynamics as a completely distinct subject and don't mention statistical mechanics if they can help it. And there's something beautiful about that. Let's face it, it's not a bad idea. Anyway, this is disturbing, but it's based, of course, on the local density approximation for chemical potential. Not quite the same as the LDA and the electronic theory that we know and love in DFT, but nevertheless, it's a local density approximation because you assume the chemical potential at any place in a material is what it would be if that place was extended infinitely in all directions with the same composition and temperature, pressure. But then from place to place, it's allowed to vary and material diffuses as a result. Now, so this is a great thing. Now I'm going to move into some, if I can move forward. Which key does it, Arash? My computer, it's that one. Let's do it.
To click on,
just the click. Okay. So now, here's a diffusion problem that Amanda, a student with us, did a few years ago, starting off a PhD thesis on an interesting problem on a drug delivery system. This was in Molly Stevens' group. They were looking at these little porous silicon spheres, which actually had gold particles in them. So they were called quantum rattles, and they were 100 or so nanometers across them. And they could pick up quantities of doxorubicin, cancer drug, and deposit it again. And it was diffusing through these little pores. And, we did some quantitative modeling comparison with the experiment, but realized we didn't know what the diffusion coefficient of this molecule was. So we'll just check it out by doing some molecular dynamics calculations. And it wasn't quite as easy as that, but this was a snapshot that when we'd done the job, reached the cover page of PCCP, and there's a doxorubicin molecule that's diffusing in a random way in water trapped between two silica slabs. And this was a model of diffusion, a confined diffusion of doxorubicin. And now, interestingly, this turns out not to be standard Brownian motion. And so that's what was sort of unexpected. And as I knew hardly anything about diffusion, I went to a symposium at the DPG, actually, where I discovered anomalous diffusion is a field. And people are doing the mathematics of it and looking at mathematical models of it. So I made contact with Ralph Metzler, whose group was doing a lot of this, and he explained a few concepts to us, which were unfamiliar to me. And anyway, the main outcome here was that what we were looking at here was subdiffusion. So just look at this right-hand panel, and you'll see there's the root mean square displacement of a molecule. There's the time along the bottom, log scale, and the slope would be 0.5 in Brownian diffusion. And in our case, it turned out to be, well, it varied according to what part of the channel the molecule was on. So Amanda was able to sort out the distance covered and the diffusion, which was of the standard Gaussian Brownian type, for certain regions of the channel. Where you were near the walls, it was very anomalous. You got a slope which was much flatter, with a time exponent much flatter. In the middle, it was much closer to Brownian. And when you combine those in the right proportions, you could reproduce the statistics of the diffusion very well. So that was my introduction to anomalous diffusion. And now I'll switch to another project on diffusion, which was complicated in a different way. And this is an ongoing project or a project area because the subject, our focus changes to different parts of the subject. But this was diffusion through an oxide scale, oxide film, which has a long history. And it was treated by the famous chemist Carl Wagner in Germany in the 1930s. And there's a beautiful formula which derived purely on thermodynamics or irreversible thermodynamic foundations, which describes the flux of oxygen diffusing through a membrane or a scale, a solid state oxide film, to be specific. And the formula that comes out with a few assumptions shows you that it is proportional to those two T's there are the conductivity or the mobility of ions and electrons, respectively. You have to have both mobilities for a scale to grow, because the transmission of ions through the scale required for it to grow has to be accompanied by a stream of electrons, holes, in order to conserve charge. Otherwise, you'd have current all the time. So that appears in the simplest way you could dream of in the formula of Carl Wagner. But this tells us nothing about mechanisms and how it works, because we wanted to know that. And of course, the engineers would like to know how you can modify it. And so Marcus set up a dynamic model of this, which was based on having a scale built of unit cells of hexagonal grains. So this is a polycrystal alumina, these are columnar grains, and of solving the surface diffusion or the two-dimensional diffusion problem down the grain boundaries, because what we've learned that Carl Wagner didn't know is that the matter is transported down the grain boundaries, not through the grains themselves. And so there's the formula again for the diffusion flux. And he solved this for 4 different species diffusing, vacancies on the sublattices of oxygen and aluminium. They're the supposed mechanism for transmission of the oxygen, the hopping of vacancies. Well, that is quite likely not true, but it's a hypothesis that we still work with. And then there's an electric field. So we could use the tools of Aveld summation to calculate the electric field and solve this on a finite difference grid. And there are lots of now time-dependent equations and graphs for how the charge develops on the surfaces of the scale and how the currents develop through the scale. But I just want to show you the bottom line, which was this graph, which is the asymptotic steady state situation where the currents are more or less stable. This was actually the assumption in Wagner's formula. And there is also in this situation some interesting power law behavior. This was measured by a Japanese group there who showed that the power law, this is a power law that describes the flux of oxygen essentially. This depends on the chemical potential of the oxygen outside the scale compared to the inside. And for high chemical potentials of oxygen, you're actually killing all the oxygen vacancies, so the diffusions by aluminium vacancies. And so the diffusion rate goes down with concentration. That's the left hand of the graph. It goes down with partial pressure of oxygen rather, and that with that power law, that's experimental -1.6. And then when the oxygen pressure is much lower, then oxygen vacancies start to dominate, and then the diffusion rate goes up with the
partial pressure of oxygen. Sorry, yes. So did I say oxygen vacancy is dominant? I meant aluminium vacancy is dominant. So Marcus's model then reproduced those two power laws in the asymptotic limits, as you can see there, his data, his computations at other points. Now I'm going to switch to the third project, which is a little more extended and ongoing and mysterious. This sort of was stimulated, brought on by work that was done by Chris Race and by Sherry Hadian, and these two gave a very nice TYC soiree in 2016 in November. And what this is about is how grain boundaries move. What's the mechanism for grain boundaries to move? And why is that important? Because moving grain boundaries cause grains to grow, or they cause them to shrink. Of course, they would like to grow thermodynamically because that reduces the interfacial area and free energy. So how do they manage to do that? What's the mechanism? Experimentally, you can see quite a lot about grain boundaries these days with electron backscattering. There's a cross-section reconstruction of a whole polycrystal, and people model them. People model grain growth. These are simulations of grain growth in a simulated polycrystal with a phase field model. Perfectly doable, but to me, the phase field model isn't actually describing any of the physics of what's going on here, except that the thermodynamics, the free energy is getting less, but the actual mechanism for making the grains grow within the model is a very unrealistic one. And I would like to just understand how it works better, and maybe lead to models that could actually predict how fast they grow. That would be nice. So let's look at a simpler problem first, because grain boundaries are more complicated than surfaces, I think you must agree. And surfaces evolve to give beautiful crystals. And these are quartz crystals, and you can see they have facets. And the facets are there because it happens that a faceted shape will minimize the free energy of a given volume of material in a single crystal structure. Particularly if it's not a metal. In a metal, the energies between different crystallographic orientations are less, but nevertheless you can get faceted metal crystals by a natural minimization of the free energy. And of course, if you have a free standing theoretical crystal, the minimum free energy shape is called the Wolf shape, where the facets are more adjusted so that they obey the Wolf construction, and that tells you that the distance of the facet from the center is inversely proportional to its surface free energy. So these crystals, by the way, I was looking for a picture of crystals on the internet, found these ones are for sale. This is a little quartz crystal cluster, costs you 16 quid. And you never guess who's selling it. You find it on Amazon, but it's in the health and beauty department of a certain store, not in anything scientific at all. Interesting, I thought. Anyway, a paradigm for the driving force of crystal grain growth has been curvature-driven growth based on surface tension, or what I prefer to call interfacial free energy, because it's not really a mechanical tension, and based on the mobility. So if you have a curvature of a surface kappa, then they might simulate it by saying that the velocity of that surface is going to move with a velocity which is proportional to a mobility, and the driving force, which is the free energy of the surface per unit area, the gamma, times the kappa, which is the curvature, which is, if it's a two-dimensional surface, it would be the mean of the radii, the principal over the inverse radii over the two principal axes. And so this can give you a beautiful simulation until, of course, your surfaces are flat, and then it stops. And then you've got to do some other tricks. But the materials theorists have thought of that. And but before we go on to that, let's just see how this can operate in practice. If you take a surface and you make a lot of parallel scratches on it, close together, and it heals up, then you can estimate from that what the surface diffusion coefficient is, which is doing the healing and reducing the surface energy. And this is an old model, goes back to Mullins. And I copied the picture out of a review, which says, well, suppose you have a sinusoidal corrugation of a surface with a wavelength lambda. How long does it take for that by surface diffusion to heal up? You know, it's a nice little problem in solving a differential equation over 2 dimensions. And the time scale for that is as I've given you there, lambda to the 4th, depends on the 4th power of the length scale, inversely on the surface energy, which you'd expect. There's inverse to the surface energy, and inverse on the surface diffusion coefficient. N there is just the density of sites on the surface. Omega is the atomic volume. So that's the length scale, and you could use that for actually making a measurement or an estimate of the surface diffusion coefficient, for example. If it's not interrupted by faceting, of course, as long as you have a surface that will do that. And to do it on real crystals is much more difficult because of the time scale is so slow. As I said in my previous slide, it might take 1,000 years to generate an equilibrium shape of a crystal a few centimeters in size. And that's because of at least partly because of that length scaling as a power to the 4th. These are nanocrystals on this picture. And these are metal, these are copper. And the experiment, this is Dominique Chatin's group in Lumini, and she could actually see facets, wolf-shaped crystals emerging on these nanocrystals, and you could make an estimate of the relative surface energies of different surfaces. It's pretty crude though, pretty crude estimate. But for this process, for them to form crystals like that, the time scale is much faster because they're so small, and it's a matter of hours at 1240 K. Interestingly, this scaling to the power 4 in these apparently such different scenarios as the surface sinusoidal corrugations and the sphere transforming into a crystal like this R to the 4th power was derived completely generally by Conyers Herring back in 1950. And he showed that such an annealing by surface diffusion will always go as the 3rd power of the length scale. And if it's, as the 4th power, and if it's volume diffusion, because of course, before you realize that surface diffusion is much faster than volume diffusion, if this was doing things by volume diffusion, then it would go as the 3rd power of the length scale. And he showed this in about 10 lines by purely dimensional but physical arguments, which I thought was a really nice paper. You know, the old papers are much easier to read. If anybody hasn't read Conyers Herring or Einstein's papers in the original, it's really worth doing because they're so much easier than modern papers. So that's crystal formation, but how does it work? Now, here's a thought experiment. Suppose we've got a wolf shape that looks like the one on the right. That's I believe it's a tetrahedron. And suppose that's the minimum energy shape. And suppose we start by cutting a cube of the same cubic materials, cubic crystal symmetry, and we wait, and presumably if we wait long enough, maybe it's the age of the universe, depends on the size of the cube we cut, presumably it'll evolve into that shape thermodynamically, but how's it going to do it? And Well, the people who do this sort of simulation of these sort of things will say, and this is a review by Marx and Peng on the nanoparticle shape. They quote a nice formula here for what they call the weighted mean curvature. This is basically the gradient of the total surface energy with respect to volume when a facet on a crystal grows outwards perpendicular to its normal, grows in the direction of its normal, sorry. So as illustrated there. And that is identified as the chemical potential of the facet, right? So, you know, the more energy that requires, the higher chemical potential the facet has. And for those of us who learned about chemical potential refers to atoms and not to facet, the idea that the facet has a chemical potential as a whole is disturbing. As a concept that provides a driving force for moving from a high total surface energy to the wolf shape or the lowest surface energy, it is certainly a valid mathematical object. The mathematics of this stuff, by the way, was developed by the amazing mathematician Gene Taylor back in 1992. Papers are quite difficult to read, but very beautiful sort of bit of topology and understanding of the mathematics of the process. But of course, these things give us no insight into how it works. And I mean, this has actually literally kept me awake at night in the past. Because with this example, how am I doing for time? On the edge. I'm nearly there. It's almost my last one, I think. Well, no, not quite, but I'll skip over this. But this is, you know, give it a much simpler example. Suppose your wolf shape is a cube, right? It's a cube. That's what the crystal wants to be, but you cut it out as a rectangle. Now, all your faces are identical in structure, free energy. So how does it know it's got to become a cube? Right? You know, just because the chemical potential of the facets might be different. Well, in this case, it's not. In fact, if we say that the cube is the equilibrium structure, all the other facets in this cubic crystal have too high an energy. And the cube is the equilibrium. Case in point might be, I suppose, magnesium oxide. That forms cubes, doesn't it? Cubic crystals. But to predict the rate of change, we actually need to know how it works. It's no good just saying, well, the free energy is lower on the right. Well, I'm sure you could do a fine phase field simulation of the process from left to right. Well, I think this is where simple diffusion is going to have to be helped along. Because here's a hypothesis. Add atoms might be launched from the corners and the edges of this object, and then they might diffuse around. But of course, thermodynamics, statistical mechanics tells us, well, their densities are going to be the same everywhere on average. The only way it can find the wolf shape is if it forms islands. So this becomes a nucleation and growth problem of islands. And the islands have got to become as big as a facet before it says, oh, look, I'm now in a slightly more cubic shape. I think I'll stay there and move on. So it'll evolve towards the cube by successive growth, nucleation and growth of islands, I think. I don't have any evidence for this, but I don't see how else it could work. Now, just to finish, well, I suppose I better finish very quickly. Chris Race's calculations and Sherry's, going back to grain boundaries. They've illustrated nucleation and growth of islands on a flat grain boundary, and suggested this as a way that it can migrate. And of course, in the simulations, to actually do this, you've got to provide some incentive, some energy reason for the facets to move. And the way this is done in simulations, I think, quite generally, is to impose an artificial potential difference between atoms in one crystal orientation compared to those on the other side in a different orientation. An artificial driving force, which is useful because you can then study mechanisms that, you know, think of fluctuation dissipation theorem or something, so that the actual fluctuations then would be in a similar structure. So that they find these islands. Now, Sherry took this a step further by looking at a faceted boundary and a driving force, and saw there that the actual process of detachment of disconnections or steps, which I think would be disconnections in this case, which detached from a facet, migrated along the smooth face and attached to the next facet, and got a whole chain of such facets moving and growing. I didn't dare try to show a movie here. I know it would go wrong. It would be chancing my luck. So the bottom line is that without treating edges and corners, I don't think you can explain wolf shape growth, and without treating the ends of these grain boundaries, where they join other grains, the triple lines as they're called, the system as a whole network of grain boundaries, triple lines, 4 points, which is where the triple lines meet, you're not going to really understand crystal growth. And so I think I've finished with that, and that's what I hope I've been doing. Thank you.
Any questions? Yes.
Should you be able to, you know, if you don't use the local density approximation for the chemical potential, how would, you know, what's the true form of explosion?
I think it's good. I think the idea is good for chemical potential if there are small deviations from equilibrium, like if there are small density variations in an old, DFT calculation. I don't think there's an equivalent of the GGA for diffusion. No. Well, would that just be a non-linear theory of diffusion? So going up to the next term, do they do that? Well, only when the driving force is on force. Yeah. I still don't know much about diffusion. I find it fascinating. Yeah,
What is the reason for subdiffusion? Is it dynamic RS?
It's the I should have said. It's the attachment and detachment of the molecule from the sidewalls. So these molecules, they move freely a bit in the channel, but then the tail gets caught on the silica at the sides. They flap about in the breeze for a bit, and then they move on. There are other examples of subdiffusion in plasmas in organic materials, which are due to some sort of viscoelasticity. Chemical reactions can also cause subdiffusion of molecules in biological systems. It would be temperature dependent, yeah. We did all these simulations at room temperature. The example you showed of how does a rectangular, cubic crystal structure become a cubic macroscopic crystal, if I understood you correctly, you were saying that that is really just a dynamical equilibrium, that there's diffusion taking place on all 6 faces, and eventually equilibrium is achieved between those 6 faces when you reach a cubic morphology.
Yeah, but I think you need island growth, don't you?
Yes.
Yes. I mean, how's it going to? It can't just be. Can't be a continuum model.
No, no.
You can't do it with any continuum model.
No. No. Any other questions? Okay, right. Well, thanks, Mike. Thank you.
Yeah. So I'm just going to conclude. So thank you very much. First of all, to all the speakers for these very exciting talks and perspective that we can have and the new challenges of material simulation. And thanks to all of you also for having been here, and also to the people that have been connected remotely. So this is the first in-presence event of the Thomas Young Center for a very long time. I think the last one was the TYC Student Day in February 2019, I suppose. Or no, 2020, I suppose. And well, let's hope that we can meet more often. So on behalf of everybody from the Thomas Young Center, many thanks again, and let's hope to continue this enterprise and to continue to be so successful in many years in the future. So there's going to be a reception now, so please stay and have a chat and so on, and hopefully see you next time to the next event, and then in a few years' time to the next milestone of celebration. Thank you.